I love my job. I'm a research geologist with the US Geological Survey, a government agency that provides earth science information to the public. Our mission, gathering data to understand how the Earth works, generally begins with exciting outdoor adventures. This summer, my adventures began with a trip down the Grand Canyon. 9 co-workers and I spent 2 weeks rafting the Colorado River through Grand Canyon National Park. Our work there is part of a program studying environmental impacts of a large dam, Glines Canyon Dam. Working downstream of the dam, we mapped landscape conditions around archaeological sites. Hundreds of archaeological sites there are affected by changes in the Colorado River's flow, sand content, and plant growth since that dam was built. The Grand Canyon is an amazing place to work. I'm sure I don't have to tell you. And the data that we provide will help determine how to manage dam-controlled flows in order to provide water and power to Arizona, Nevada, and California, but also to minimize the negative impact that these unnatural flows have on a spectacular national park. After the Grand Canyon trip, our next adventures took us to 2 places where large dams have just been taken down. One is close to here in the Carmel Valley, where the largest dam removal in California took place last fall. We measured channel topography upstream and downstream of the old dam site there because we want to understand how landscapes and their ecosystems, especially fish habitat here, adjust after a disturbance like taking out a big dam. After that, I went up to the Elwha River in Washington State, where the world's largest dam removal took place. My colleagues and I have been working there for 10 years, measuring the stream channel and how it's changed before, during, and after 2 huge dams were demolished. Those dams were taken out to allow migratory fish access to many miles of habitat that they couldn't access for 100 years with those dams in place. This Elwha River project is one of the largest environmental restorations going on nationwide, and it has been so exciting to be part of that for 10 years and to see this beautiful place being restored to a more natural condition. Our last work adventures of 2016 involved spending 18 days on a ship offshore of Alaska. Working around the clock in 12-hour shifts, our research team mapped a large offshore fault zone. It's called the Queen Charlotte Fault, and it marks the boundary between the Pacific Plate and the North American tectonic plate. This fault can produce earthquakes of magnitudes 8 and higher, which can generate a tsunami, but the fault had never been mapped in detail until now. We will use these new data to better understand earthquake and landslide and tsunami hazards in that area in order to better prepare and protect coastal communities for those types of geologic events. Each of these projects and the goals we're working toward and the adventures that my team and I get to have doing the work are all part of trying to understand different aspects of how humans and our planet interact. So how did earth science or geology get started? Well, for thousands of years, people have looked around where they lived and been curious as to the origins of the landscape around them. Along with human curiosity about other aspects of the natural world, people wondered, for instance, why are there mountains over there and why are they shaped the way they are? People have long sought explanations for geologic disasters that affect their communities, floods and earthquakes and so on. And people noticed fossils preserved in rocks and wondered what had happened and how much time went by to have erased earlier life forms, leaving only bones and rocks. These are fascinating questions about the very basics of our planet that interested not only ancient people, but many of us today. Explanations based in spirituality were the norm for many generations. For a long, long time, people attributed geologic processes to benevolent or angry gods that would pay us back for human actions. By the 1800s, the start of a systematic scientific approach began to reveal aspects of Earth's past that at first seemed far-fetched. So, could the area where Boston is today once have been covered by a mile-thick ice sheet? That sounded like a crazy idea at first, but the more scientists studied that landscape, the more it began to make sense that it had been shaped by ice. Or, could the continents move around? There was plenty of debate about that until the evidence became overwhelming that yes, the motion of tectonic plates changes the positions of land and ocean greatly over long time periods. With advances in geologic studies, our long legacy of human curiosity gradually led to some profound insights about the Earth. By the 1960s, humanity had had two huge breakthroughs in understanding our planet. Those breakthroughs resulted from advances in geophysics and geochemistry, so especially being able to map out precisely where and how earthquakes happen, and being able to measure dates in Earth history more accurately than ever before. One of those breakthroughs was the concept of deep time, or geologic time. That our planet has been found to be 4.5 billion years old is shocking to a human mind that normally thinks in terms of days, weeks, months, and years. If we imagine all of Earth history scaled to fit on a 24-hour clock, the concept of deep time becomes truly mind-boggling. If the Earth coalesced into a planet at 12 a.m., then dinosaurs first appeared around 10:45 p.m. and died out less than an hour later. The entire legacy of human history, our species as we know it, spans less than 2 minutes before midnight. The second major breakthrough we had was to understand plate tectonics. We finally understood that the Earth's surface is unstable and plates shift in ways that are broadly predictable, although we still can't predict individual earthquakes or volcanic eruptions in detail. And as our understanding of the planet's history and processes accelerated, so too did our need for this type of information. Over the past 200 years, we humans have greatly increased our need to extract resources from this planet, and our population has grown so much and so fast that human interaction with the Earth is much greater now than in any past generation. Today, many areas of Earth science are progressing, but there has lately been an especially large effort to understand Earth surface processes better, so rivers, glaciers, landslides, and so on, partly because of links between those processes and climate change. Realizing that humans can and do affect our climate is one of the most important scientific findings of our time, and probably our third major breakthrough in this field after deep time and plate tectonics. So with advances in geologic and climate studies, our long legacy of human curiosity has led to profound realizations that have really only happened in the past generation or two. We still have much to learn about climate change and human influence on the Earth and how that will play into the legacy that we leave to the next generations. But our capabilities of gathering data to understand these problems are greater now than ever, as is our need for this type of knowledge. Almost half the people on Earth live in coastal areas worldwide. Our tendency to live in coastal zones means that sea level rise due to climate change, as well as certain geologic hazards like tsunamis and hurricanes that disproportionately affect coastal areas, is a much greater cost to humanity now than it has ever been. Even away from the coast, the human and the economic cost of geologic hazards is great and growing. So in addition to the need for better climate and landscape science, we need better science on geologic hazards now more than ever. Consider our home state of California, where the Earth is notoriously unstable. California has it all in terms of geologic hazards. We have earthquakes, landslides, tsunamis, we have floods, droughts, coastal storms, even volcanoes up north. The last time there was a major earthquake in the Bay Area in 1906, less than 500,000 people lived here. And in that 1906 earthquake, approximately 1% of the San Francisco population was killed, and about half the population became homeless. Today, the Bay Area population is more than 15 times greater than in 1906, and there's roughly a 50% chance of a magnitude 7 earthquake happening there in the next 3 decades. But there are definitely things we can do to prepare for those hazards, knowing where and how to build, and so on. Keeping people safe often starts with good earth science. Earth science is also part of global planning for food security. The human population will surpass 10 billion in your lifetime, and how do we feed 10 billion people? We need to understand as much as we can about earth processes that affect food production. Floods, drought risk, landscape stability, especially in very dry or very wet regions where people are trying to produce food. Earth scientists also work closely with ecologists to preserve and restore ecosystems, which is one of the most enjoyable aspects of my job. The more we understand about how geologic processes and ecosystems interact, the better we can take care of our planet. So what's it like to be an earth scientist? Working in this field is fascinating and a lot of fun most of the time. There are many opportunities for travel, adventure, time outdoors, and an earth science career is a unique contribution to understanding some important problems facing our planet and finding ways to address those problems. We do have a pressing need for greater diversity in earth science as well as in other STEM fields. We've made progress, but we still need more diversity in order to make sure that we're doing the best work. The importance of diversity goes well beyond the concept that just giving everyone equal opportunities is the right thing to do. It absolutely is, but more than that, the whole process of doing science improves when the participants are more diverse. By analogy, after Major League Baseball integrated in the 1940s, statistics of Major League Baseball games, analyzed by a biologist, Stephen Jay Gould, showed that the quality of the game improved measurably. Baseball became a better game when the best players, not just the best white players, were playing the game with and against each other in the same leagues. In the same way, doing the best possible science requires drawing from the biggest possible talent pool of women, minorities, and so on, to make sure that we're getting the best ideas and the best insights. You don't have to be a full-time scientist, though, to more fully enjoy and understand the Earth or to contribute to addressing important issues like climate change or geologic hazards. We need people of every professional calling, educators, government officials, urban planners, and so on, to appreciate our planet and the human role in it. We're all taking part in this adventure of living on a fascinating planet Earth. We're continuing a legacy of 10,000 generations of human curiosity about where we live. Stay curious, go outdoors, look at the landscape and wonder how it got to be that way. Stay in awe of our incredible planet. Thank you.